In this video, we will delve into the concepts of bindings, routing keys, and exchanges in RabbitMQ. These fundamental components play a crucial role in message routing and distribution within the RabbitMQ messaging system. In RabbitMQ, bindings are used to establish connections between exchanges and queues. An exchange is a message routing component that receives messages from producers and distributes them to queues based on certain rules. A queue, on the other hand, is a buffer that holds the messages until a consumer retrieves them. Bindings define the rules for message routing from exchanges to queues. When a binding is created between an exchange and a queue, it specifies how messages should be delivered from the exchange to that particular queue. These rules can be based on criteria such as message attributes, routing keys, or headers. By creating bindings, you enable the flow of messages between the producer and consumer components in RabbitMQ. When a producer sends a message to an exchange, the exchange uses the binding information to determine which queues should receive the message. The message is then delivered to the bound queues, where it can be consumed by the consumer component. Overall, bindings in RabbitMQ play a crucial role in connecting exchanges and queues, establishing the rules for message routing, and facilitating the communication between producers and consumers in a messaging system. Bindings in RabbitMQ can have properties that provide additional rules and behavior. These properties allow you to customize the behavior of the bindings to suit your specific requirements. Here are some common properties of bindings. Durability. Durability ensures that bindings persist even if RabbitMQ restarts. By default, bindings are durable, meaning they survive a server restart. This is important because if a binding is lost during a restart, messages may not be routed correctly. With durability, you can ensure that the bindings remain intact and the message routing continues seamlessly after a restart. Exclusivity. Exclusivity restricts bindings to specific consumers or connections. By making a binding exclusive, you can ensure that only a specific consumer or connection is able to receive messages from that binding. This can be useful in scenarios where you want to limit the consumption of messages to a particular consumer or connection, such as implementing a task queue where only one consumer should process the messages. Auto-deletion. Auto-deletion is a property that automatically removes bindings when they are no longer in use. When a binding is no longer needed or is no longer receiving messages, it can be automatically deleted to free up resources. This feature helps in managing the lifecycle of bindings and preventing unnecessary clutter in the RabbitMQ server. In RabbitMQ, the routing key is an attribute assigned to a message by the producer. It serves as a piece of information that helps exchanges determine how to route the message to the appropriate queues. When a producer sends a message to an exchange, it includes a routing key along with the message. Exchanges in RabbitMQ receive messages from producers and then distribute them to queues based on specific rules and criteria. One of the key factors in this routing process is the routing key. Exchanges match the routing key of a message to the bindings that have been established between the exchange and the queues. Bindings define the relationship between exchanges and queues and specify the rules for message routing. They can be created with various criteria such as routing keys, message attributes, or headers. When an exchange receives a message, it examines the routing key of the message and compares it with the routing keys specified in the bindings. If there is a matching routing key in a binding, the exchange will route the message to the queue associated with that binding. In other words, the exchange uses the routing key to determine which queues should receive the message. This allows for flexible and selective routing of messages based on their routing keys. The routing key serves as a way to categorize messages and control their flow within the messaging system. It enables exchanges to make informed decisions on how to route messages based on the bindings that have been established. In RabbitMQ, the direct exchange and topic exchange are the two types of exchanges that use routing keys for message routing. Direct exchange. The direct exchange uses the routing key as the main criterion for message routing. When a message is sent to a direct exchange, the exchange compares the routing key of the message with the routing keys specified in the bindings. If there is an exact match between the routing key of the message and the routing key in a binding, the message is routed to the corresponding queues bound to that routing key. Topic exchange. The topic exchange also utilizes routing keys, but in a more flexible and pattern-based manner. In this type of exchange, the routing key is treated as a string containing multiple words or segments separated by dots. Example: stock.usd.nysc. The bindings in a topic exchange can use wildcard characters to match patterns in the routing keys. The most common wildcards used are asterisk, matches exactly one word, and hashtag, matches 0 or more words. The topic exchange compares the routing key of a message with the routing key pattern specified in the bindings, and the message is delivered to the queues that have bindings matching the pattern. This code demonstrates how to create bindings between an exchange and a queue in RabbitMQ using the Pika library in Python. It declares an exchange, a queue, and creates a binding between them, allowing messages to be routed from the exchange to the queue based on the specified routing key. First, we establish a connection to the RabbitMQ server using pika.blocking connection. Then, we create a channel using connection.channel. We declare an exchange named my_exchange of type direct using channel.exchange_declare. We declare a queue named my_queue using channel.queue_declare. Next, we create a binding between the exchange and queue using channel.queue_bind. We specify the exchange name, queue name, and routing key. We publish a message to the exchange using channel.basic_publish. We provide the exchange name, routing key, and message body. Here's a simplified flowchart illustrating the relationships between connection, channel, exchange, binding, and queue in RabbitMQ. A connection is established between the client and the RabbitMQ server. A channel is created within the connection. Channels act as virtual connections that can multiplex different tasks and operations. The channel declares an exchange, specifying its type and optional parameters. The exchange is responsible for receiving messages from producers and routing them to queues. The channel creates a binding, which specifies the relationship between the exchange and a queue. The binding typically includes criteria such as a routing key or pattern to determine how messages should be routed from the exchange to the queue. The queue is declared and bound to the exchange using the binding. The queue acts as a buffer that holds the messages until a consumer retrieves them. Messages produced by publishers are sent to the exchange, which uses the binding information to determine which queues should receive the message. The message is routed from the exchange to the bound queues based on the criteria specified in the binding. Consumers can then consume the messages from the queue. A connection can have multiple channels. This is because channels are lightweight and do not require a lot of resources. This allows applications to create multiple channels for different purposes, such as publishing and consuming messages, or performing administrative tasks. The number of channels that can be opened on a connection is limited by the server's configuration. The default maximum number of channels is 64, but this can be increased by setting the channel_max configuration option. It is important to note that channels are not persistent. When a connection is closed, all of the channels on that connection are also closed. This means that any data that was not explicitly persisted will be lost. Here are some additional details about connections and channels in RabbitMQ. A connection is a TCP connection between an application and the RabbitMQ broker. A channel is a lightweight connection that is used to perform operations on the broker, such as publishing and consuming messages. Channels are not persistent. When a connection is closed, all of the channels on that connection are also closed. The number of channels that can be opened on a connection is limited by the server's configuration. Here's a detailed diagram illustrating the connection between an exchange, a binding, and a queue in RabbitMQ. Exchange represents the message routing component in RabbitMQ. It receives messages from producers and routes them to queues based on rules defined by bindings. Binding establishes a connection between an exchange and a queue. It defines the routing rules for message delivery from the exchange to the queue. Queue acts as a buffer that holds messages until they are consumed by consumers. Messages are routed to the queue based on the rules defined in the binding. The diagram visually demonstrates the relationship between an exchange, a binding, and a queue in RabbitMQ. The exchange routes messages to the appropriate queue through the binding, which specifies the rules for message routing. The queue holds the messages until they are consumed by consumers. Here's a vertical chart illustrating the relationship between a queue and multiple consumers in RabbitMQ. The queue acts as a buffer that holds messages until they are consumed. Multiple consumers can be connected to the same queue to process messages concurrently. Each consumer independently retrieves messages from the queue. Consumer 1, Consumer 2, and Consumer 3 represent multiple consumers that are at the same level and can consume messages from the queue simultaneously. Each consumer operates independently and processes messages based on their own availability and processing capacity. This capacity graph visualizes the varying load distribution among different consumers over time. Each consumer's capacity is represented by the height of their respective column, indicating their ability to handle the load. The graph illustrates how the load can be distributed among consumers based on their individual capacities, allowing for efficient resource utilization and load balancing in RabbitMQ. This diagram demonstrates the flow of messages in a direct exchange scenario in RabbitMQ. The producer sends messages to the direct exchange, which routes the messages to the appropriate queue based on the provided routing key in the binding. The consumer then consumes the messages from the queue, ensuring that only messages with the matching routing key are received. This diagram demonstrates the relationship between a producer, a fanout exchange, and multiple consumers in RabbitMQ. The producer sends messages to the fanout exchange, which broadcasts the messages to all connected consumers. Each consumer operates independently and consumes messages from the fanout exchange. In a fanout exchange, messages are distributed to all bound queues without any routing key rules. It operates based on a publish-subscribe model, where messages are broadcasted to all connected consumers regardless of any specific routing criteria. When a message is published to a fanout exchange, the exchange simply broadcasts the message to all queues that are bound to it. The fanout exchange doesn't consider any routing keys or patterns because its purpose is to deliver messages to all connected queues indiscriminately. This behavior makes the fanout exchange ideal for implementing a publish-subscribe messaging pattern. It allows publishers to send messages without specifying any specific routing rules, and all consumers that are bound to the exchange will receive a copy of each message. It's important to note that the fanout exchange does not evaluate routing keys or perform any kind of filtering. Instead, it focuses on distributing messages to all connected queues in a one-to-many fashion. This approach enables the fanout exchange to provide a straightforward and efficient way to implement broadcasting-like messaging scenarios in RabbitMQ. This diagram illustrates the flow of messages in a header exchange scenario in RabbitMQ. The producer sends messages to the header exchange, which routes the messages to the appropriate queues based on matching headers specified in the bindings. The consumer then consumes the messages from the queues based on the specified headers. The header exchange allows for flexible and selective message routing based on header values, enabling more complex routing criteria compared to other exchange types. RPC, Remote Procedure Call, is a communication pattern used to enable interaction between distributed systems or components. It allows a client component to invoke a method or function on a remote server component and obtain the result. In the context of RabbitMQ, the RPC pattern can be implemented using a combination of queues and direct communication between a producer and a consumer. Here's how it works. The client, also known as the producer, sends an RPC request message to a queue, typically known as the request queue. The consumer, which acts as the server, listens to the request queue and receives the RPC request message. The consumer processes the RPC request, executes the necessary logic, and generates the result. To send the result back to the client, the consumer creates a unique reply queue and includes the reply queue address as part of the RPC request message. The consumer sends the RPC request message, including the reply queue address, to another queue known as the reply to queue. The client producer consumes messages from the reply queue, waiting for the response. The consumer server sends the result of the RPC request as a message to the reply to queue. The client producer receives the response from the reply queue, obtaining the result of the RPC call. The client producer can continue its processing based on the obtained result. We will explore the command line interface CLI tools provided by RabbitMQ for managing and administering the messaging system. We will learn about the following CLI tools. RabbitMQ RabbitMQ Control. This tool allows us to manage and administer RabbitMQ instances using various commands. It provides capabilities to manage exchanges, queues, bindings, users, permissions, and more. With RabbitMQ we can also monitor and troubleshoot RabbitMQ instances and perform cluster management and configuration. Rabbit Diagnostics. This CLI tool is specifically designed for diagnosing and troubleshooting RabbitMQ. It offers diagnostic commands to check the health, status, and configuration of RabbitMQ nodes. It assists in identifying potential issues, bottlenecks, misconfigurations, and aids in troubleshooting connectivity problems and performance optimizations. Rabbit Plugins. With this CLI tool, we can manage plugins in RabbitMQ. It allows us to enable, disable, and list the installed plugins. By using Rabbit Plugins, we can enhance RabbitMQ functionality by adding additional features and capabilities. It provides customization and extension options for RabbitMQ. Rabbit Queues. This CLI tool enables us to manage queues in RabbitMQ. It supports operations such as declaring, deleting, purging, and inspecting queues. Rabbit Queues provides valuable information about queue statistics, message counts, and consumer details. It facilitates monitoring and management of queues in RabbitMQ instances. RabbitMQ Streams. RabbitMQ Streams is a CLI tool that allows us to work with RabbitMQ Streams. RabbitMQ Streams is a log-based messaging system built on top of RabbitMQ. With this tool, we can publish, consume, and analyze streaming data within RabbitMQ. It provides commands for managing streams, creating publishers and consumers, and querying stream information. RabbitMQ Upgrade. This CLI tool simplifies the process of upgrading RabbitMQ to a new version. It assists in handling backup, migration, and compatibility aspects during the upgrade. RabbitMQ Upgrade provides guidance and commands for a smooth and successful upgrade process, ensuring the preservation of data and configuration.